Hello MCT4C, we're looking at polynomial functions day 5, and we're continuing with properties of odd and even functions. We're going to be looking at 3 functions today. We're going to start by discussing the end behaviors of these functions. I have written them as tables of values. So we're going to first look at the end behaviors of these functions by making educated guesses. So as I look at my table of values, and I want to look as x approaches infinity, and then we'll look as x approaches negative infinity, just by observation. So not terribly mathematical. But we look as x gets larger, it kind of looks like y is getting larger. We look as x approaches negative side of things, and it kind of looks like y is getting bigger again. For this one, let's look at the end behavior. As x gets larger, it looks like our function might be getting small. As x approaches negative infinity, by observation, it does appear that the function is approaching negative infinity as well. Let's look at the degrees of these two functions and see if what we have observed makes sense. If we go back to grade 9, we did a lot of first and second differences to look at tables of values. I'm going to look at my first differences. So we would do negative 5 take away 2, negative 7. We have negative 8 take away negative 5, negative 3, negative 1, or sorry, positive 1. Negative 2 take away negative 7 is 5, 9, and 13. So I've just subtracted subsequent pairs. So my first differences are not the same. This is not linear. Now we know from grade 10, if our second differences were the same, then we had a quadratic. So we're going to take our first differences and we're going to subtract those. Okay, so negative 3 take away negative 7 is positive 4. Positive 1 take away negative 3 is 4. 5 take away 1 is, oh, interesting, 4, 4, 4. Our second differences are the same. So since the second differences are the same, we have a quadratic. And we know that that end behavior follows a quadratic. We know that our degree is 2. And it is even because of this observation of the end behavior. Our second differences are the same and they're positive. We're going to do the same for this second set of values. This function, our first differences. Now look at each pair. Negative 20 take away negative 45 is 25. Negative 3 take away negative 20 is 17. 9, 1, -7, and -15. Those first differences are not the same. It is not a line. Second differences. I'm going to be comparing my first differences. 17 take away 25 is -8. 9 take away 17 is -8. 1 take away 9, -8, -8, -8. Our second differences are equal, so it's a quadratic. Our second differences are negative, that means it's upside down. Our leading coefficient is going to be a negative number. The end behavior follows. We have an even because it has degree 2, quadratic, negative, quadratic function. And the end behavior should follow what we saw in our observations yesterday. The third one, I have my table of values. I'm going to look at the first differences. Oops, let's not do black. First differences. I have a -3, -7, -5, 3, 17, 37. They're not the same. It's not a line. Second differences. -7 take away -3 is -4. -5 take away -7 is 2, 8, 14, and 20. Looking at the second differences, they are not the same. It is not a quadratic. Third differences. We're going to look at that, and that. 2 take away -4 is 6. 8 take away 2 is 6. 14 take away 8 is 6. 20 take away 14 is 6. Our third differences are the same. This is a cubic. It appears, if we are to eyeball this thing, that as x gets very, very large, our function is getting large. It appears that as x is approaching -infinity, our function is becoming less negative, is increasing towards positive infinity, just by observation. We're going to see if this is going to hold with the same end behavior. Our third differences are positive. So we have an odd, because it's cubic, because our third differences are the same. Positive function, because those third differences are +6. That end behavior holds with our summary chart for that. Is it possible to determine the equation of each of those functions that we've looked at? It is. It is a little bit tricky. Let's look at the first one. We knew that it was a quadratic. We knew, just going to go back to it, we knew that the y-intercept is right there. That's information that we could use. So we will use that y-intercept. We also remember from that first table of values that we knew it was quadratic because we found the second differences were the same. Those second differences were 4, positive. So we know that our quadratic is going to open upwards. Our a is going to be positive. But what is a? If you remember from grade 10, when we had our basic y equals x squared, and we looked at the second differences were all 2. I'm going to put this normally in quotes. For your basic y equals x squared, your second differences are 2. So if our second differences are 4, then our a value is double that. So we have the a value and we have a y-intercept. So we know that our function looks like y equals 2x squared plus bx minus 7. If we had one other point, we could substitute wait a minute, we do. We can substitute a point, any point you like. I've chosen this one. We're going to substitute our y value here, x value there. 2 equals 2 times minus 3 squared plus b times minus 3. Subtract 7. We're going to solve for b. 2 equals. Order of operations says we do that first. 2 equals, we're going to do this somewhere else, 18 plus b times negative 3, take away 7. 2 equals 11 plus b times negative 3. Subtract 11 from both sides. Divide both sides by negative 3. Our b value is 3. Final equation. Y equals 2x squared. Because our second differences were double the normal second difference. We solve for the b, and we know our y-intercept. That's our equation for a. B was also a quadratic. So we know it is going to look like y equals ax squared plus bx plus c. We look back on our table of values, the y-intercept. I like the y-intercept. And that will give us our c value for the equation of our quadratic. Our second differences were minus 8. Normally for a quadratic, your second differences are 2. So that gives us our a value as minus 4. So we know so far that the equation of our quadratic will be y equals minus 4x squared plus bx plus 6. We're going to substitute a point. I like the point 2, 0. I'm going to substitute that into the equation and solve for b. So 0 is here. 2 goes wherever you have an x. And we will solve. Remember to do order of operations. We do the 2 squared first. Minus 4 times 4 is minus 16 plus 2b plus 6. We have 0 equals minus 10 plus 2b. Add 10 to both sides. Divide both sides by 2. And we have b equals 5. Final answer, y equals minus 4x squared plus 5x plus 6. Who knew? Last, we know this one is going to be harder. It's a cubic. Y equals ax cubed plus bx squared plus cx plus d. Here's a little gift for you. For quadratics, your normal second differences are 2. For a cubic, we know that we're looking for the third differences to be the same. And the third differences are normally 6. Maybe you'll make note of this as well for a quartic. Normal fourth differences, which is what you would be looking for a quartic, are 24. So that you can keep as an aside. Interesting information. All right. We had a cubic. We looked at the table of values and we noticed that our y-intercept was 1. Our third differences are 6. So a equals 1. Normal third difference for a cubic is 6. Anyways, so our a is 1. So far we have y equals 1x cubed plus bx squared plus cx plus 1. I'm going to substitute a point. Let's choose 1, 4. So I'm going to substitute that point into my equation, and I will have okay, just going to tidy that up a little bit. 4 equals 1 plus b plus c plus 1. 2 equals b plus c once I get rid of both of my 1's. That's not entirely what I wanted. So I'm going to do it again. I am going to substitute a different point and see what happens. Let's do 221. So 21 equals 2 cubed plus b times 2 squared plus c times 2 plus 1. Tidy it up. We're going to have 21 equals 8 plus 4b plus 2c plus 1. 21 take away 9 is 12. I guess I could make that a little prettier by dividing everything by 2. So I have not a final answer that I want, but I do have 2 equations with 2 letters of the alphabet, 2 equations and 2 unknowns. We can solve that. I'm going to grab a little space down here at the bottom so that I can find values for b and c so that I have the equation for my cubic. 2 equals b plus c, and at the same time 6 equals 2b plus c. I can solve both of those. I'm going to rearrange this one and do substitution. I'm going to isolate b by subtracting c from both sides. I'm going to substitute that into my other equation, and wherever I see a b, I'm going to write 2 minus c instead. Let's tidy that up for c. Little arrows help every time. 6 equals 4 minus c. Subtract 4 from both sides. C is equal to negative 2. If c is equal to negative 2, then b is equal to, I'm putting a negative 2 right here, is equal to 4. Are both of these true if b is 4 and c is negative 2? Yes. Yes. I have found my values for b and c. Finally, we have our equation for that cubic. Y equals 1 x cubed plus my b value is 4 plus my c value is minus 2 and my y-intercept was 1. That is the equation of our cubic. I have homework questions here for you. I gave you a little discussion bubble on one of the questions where we were asking about restrictions on the domain. Just be careful. If you have a real-life application, such as time for this soccer ball, doesn't make sense to have time as negative number. So we just want to be careful with our restrictions if you have a real-life application.